All right. In this learning objective, we're using conservation of angular momentum, where we're looking at the initial moment of inertia of the system, and its initial rotation rate is equal to its final moment of inertia and its final rotation rate. We talked about examples in class where changing the moment of inertia by simply changing how the mass is distributed relative to the rotation axis can affect the rotation rate. In this problem, we're using a merry-go-round as our system, which is a playground equipment. Ours seems to be rather unsafe because I didn't put any sort of handles or bars on for kids to hang on to. It's a free-for-all. But we're going to model our merry-go-round as a flat uniform disc. It has a radius of 1.75 meters and a total mass of 75 kilograms. It's rotating initially at the brisk rate of 15 RPMs around a vertical axis through its center. It's just as we would expect. And we have a small child is close to the center of the merry-go-round. The child has a mass of 20 kilograms, and he's only 10 centimeters from the center. If the child moves very carefully to a new position, so we're going to put him, so this is where he is initially. In the final situation, he's going to move to here, where the distance from the edge is 10 centimeters, and we want to find the new rotation rate. So what we want to be doing is looking at how the moments of inertia are changing. So let's look at the initial moment of inertia. The initial moment of inertia is the inertia of the merry-go-round plus the inertia of the child. The merry-go-round we treat as a disk, so its moment of inertia is 1/2 mr squared. But the child we're going to treat as a point mass, so his moment of inertia is just mr squared. If we put in the values that we know that apply here, the mass of the merry-go-round is 75 kilograms, its radius is 1.75. The child has a mass of 20 kilograms, and initially he's 10 centimeters from the edge. This gives us an initial moment of inertia of this system of 115 kilograms meters squared. Now, in the final situation, we still want to do the merry-go-round and the child, but the values are going to change because the child has moved to a new location. The moment of inertia of the merry-go-round does not change. So if you had done that calculation, that was 114.8 for the merry-go-round. Now the child has a new location. His radius is now 1.65 meters from the center. And so that's going to really affect the overall moment of inertia, make it a little bit bigger. We get a moment of inertia of 168.95 kilograms meters squared. So this increase in the moment of inertia should also bring on a decrease in rotation rate. So I rearranged the conservation of angular momentum here to solve for the final angular velocity. And I wanted to just mention that in this case, because we're just taking the original angular velocity and we're multiplying it by a ratio of moments of inertia, which end up being, this will be a pure number, I could actually keep the rotation rate in RPMs. So if I use 115 as the original moment of inertia and 168.95 as the final, and then I could actually use 15 RPM as the initial rotation rate, and when I find and solve for this I get 10.1, and this is also RPM. So I know we usually tell you to change units. This is a case where you actually don't have to. Definitely though, if you'd prefer, you could have changed 15 RPM into radians per second and have that answer in the final case in radians per second. It's perfectly fine. I wanted to sort of show you, in this case, because we're not multiplying this omega by any term that has units, because this is just a ratio of two values, so then it's just a pure number with no units. It doesn't really affect, we can keep the units of omega. All right.